India has set a hard target to scale its nuclear capacity to 100 gigawatts by 2047. That demand is being driven directly by the continuous 24/7 power requirements of heavy industry and a rapidly expanding footprint of hyperscale data centers. This chart maps the problem. A rising curve shows the trajectory to 100 gigawatts. To hit that output, the fuel constraint is staggering. 18,000 to 20,000 tons of uranium are required annually. That volume vastly exceeds India's total domestic reserves. To put that in perspective, 20,000 tons represents roughly 1/3 of current global uranium production. Importing that much fuel concentrates risk across a narrow international supply chain, creating a severe geopolitical vulnerability. The alternative lies right on the coastline. The monazite sands in Kerala and Tamil Nadu contain an estimated 500,000 tons of thorium. True energy autonomy requires decoupling from a uranium-dependent market. India has to build the mechanical infrastructure to process and burn thorium. This graphic breaks down the core physics constraint. On the left is uranium-235, which is highly fissile. On the right is thorium-232. Thorium is abundant, but it is only fertile. Being fertile means it cannot spontaneously sustain a nuclear chain reaction. You cannot simply load raw thorium into a conventional reactor to generate power. To make it useful, the thorium must be bombarded with neutrons. This specific interaction transmutes the fertile thorium-232 into uranium-233, an isotope that is highly fissile. That transmutation does not occur naturally. It has to be engineered inside a highly specialized, closed nuclear fuel cycle. Without the precise conditions to continuously convert and burn the fuel, the chain reaction will starve and fizzle out. The entirety of India's multi-decade nuclear roadmap is constructed around this single limitation. It is an elaborate, three-stage mechanical workaround designed to force thorium to burn. Stage 1 of this architecture relies on India's legacy fleet of pressurized heavy water reactors, or PHWRs. This diagram illustrates the Stage 1 flow. Natural uranium, mostly uranium-238, is fed into the reactor to generate baseload electricity. But electricity is a secondary benefit. The true mechanical purpose is what happens to the spent fuel. The reaction breeds a secondary material, plutonium-239. Stage 1 operates essentially as a manufacturing plant. It produces the exact isotope required to ignite the next phase of the cycle. That brings us to Stage 2, physically realized here at the 500 megawatt prototype fast breeder reactor in Kalpakkam. Looking at a cross-section of the fast breeder core, the center is loaded with the plutonium-239 harvested from Stage 1. Engineers wrap it in a blanket, initially made of fertile depleted uranium. As the plutonium reacts, it releases fast neutrons that bombard the surrounding blanket, transmuting it. The reactor breeds more fissile material in the blanket than it consumes in the core. Once enough excess plutonium is amassed, operators execute a critical pivot. The depleted uranium blanket is swapped for thorium-232. Fast neutrons now bombard the thorium, transmuting it into uranium-233. Achieving criticality in this specific reactor proves the concept. It demonstrates that the physics to run an entire economy on thorium actually work at scale. To make this cycle sustainable over decades, you have to deal with the spent fuel. That requires actinide partitioning. This schematic shows the partitioning process. Chemical separation extracts the highly radioactive, long-lived waste, known as actinides, from the spent fuel. Instead of burying these toxic elements, the waste is fed directly back into the fast reactor, where fast neutrons incinerate it. You separate the hazard, route it back into the high-energy core, and force it to undergo fission. The loop is closed. The system actively converts ecological liabilities into usable fuel, locking in long-term sustainability for the power grid. This timeline tracks India's capacity projections. While the Stage 2 fast breeder achieves criticality in 2026, the commercial rollout of Stage 3 advanced heavy water reactors won't scale until much later. That leaves a vast gap in the middle. Waiting for Stage 3 to mature organically makes it mathematically impossible to hit the 100 gigawatt capacity target by 2047. To bridge this deficit, planners are accelerating small modular reactors. This includes indigenous designs like the Sukma, a 10-megawatt microreactor targeted for 2031, with a 15-year thorium cycle. Simultaneously, joint ventures like the Russian SVBR-100 are evaluated to integrate thorium fuel into modular architectures. SMRs bypass the decade-long construction times as massive conventional plants. They are factory-built, shipped to the site, and installed in parallel. These modular units are not replacing the three-stage architecture. They are an acceleration vector, deploying thorium commercially to meet the demand curve, while the larger Stage 3 reactors are finalized. Building out that infrastructure requires immense capital. The legislative mechanism to secure it is the Shanti Act, passed in December 2025. The act dismantles a 60-year state monopoly. It strips away supplier liability clauses that previously stalled international contracts, and it opens the sector to 49% foreign direct investment. The objective is strictly financial. The state needs to mobilize an estimated 15 to 20 lakh crore in private equity to build raw gigawatt capacity. This graphic shows the reform's exact boundary. Private investors are authorized to fund, build, and operate power generation assets, but the nuclear fuel cycle remains siloed. The government retains exclusive, sovereign control over uranium enrichment, spent fuel reprocessing, and heavy water production. By transferring the massive financial risk of construction to the private sector, the state accelerates its grid expansion. At the same time, it permanently guards the specific physics and closed-loop engineering required to achieve total